Welcome to Science with Mr. Morgan. In today's episode, we're going to be learning about what's beyond our solar system. Kind of. On the screen, you will see an image of the life cycle of a star. And let's go over quick before we break it down further. So starting with the stellar nebula, a star can become an average star, or a massive star. If it becomes an average star, it will eventually become a red giant, followed by a planetary nebula, and eventually a white dwarf. If it becomes a massive star, it will eventually become a red supergiant, then a supernova. And depending on the size of the star, or the amount of mass it has, it will either become a neutron star or a black hole after a supernova occurs. But now let's dive into that a little bit deeper and start at the very beginning, the birthplace of stars. So a nebula, otherwise known as the stellar nursery. Imagine a massive cloud of gas and dust floating in space. This is a nebula, the cosmic nursery where stars are born. Made mostly of hydrogen and helium, these clouds exist in a delicate balance. Gravity pulls everything inward, while temperature and pressure push outward, keeping the cloud stable and in equilibrium. But what happens when this balance gets disrupted? Well, a nearby star could explode, or two stars could collide, which sends shock waves spreading throughout the nebula. When that happens, gravity takes over and causes parts of a nebula to collapse in on itself, forming dense pockets of gas and dust. As these pockets shrink, they heat up, because everything's colliding. Once the temperature reaches about 10 million degrees Celsius, something incredible happens. Nuclear fusion begins, and a new star is born. Now, what exactly is nuclear fusion? Well, this was covered in another episode entirely, but as a refresher, nuclear fusion is the process where atoms of hydrogen smash together and form helium, releasing massive amounts of energy. And this process is what fuels the star, allowing it to shine for millions to billions of years. But what happens when a star runs out of fuel? Well, that really depends on how much mass it has. So you have low mass stars and high mass stars. And first, let's take a look at low mass stars. Our sun is a good example of a low mass star, meaning that it has a predictable life cycle. It starts as a main sequence star, steadily fusing hydrogen into helium. Eventually, that hydrogen is going to run out. And when that happens, the core contracts while the outer layers expand, which forms a red giant. Eventually, the outer layers drift away and leave behind what's known as a white dwarf. After 1 billion years, give or take, the white dwarf ends up cooling down, fading, and becoming a dark, cold object in space. But those outer gases that drift away, what about them? Don't worry, they don't go to waste. They become raw materials for future stars to form. Now we also have high mass stars, and these high mass stars end up being a lot more dramatic when they reach the end of their life. Instead of gently fading away, it ends up exploding in a spectacular event known as a supernova. Now, these high mass stars go through the following steps. Originally, it ends up expanding into a red supergiant. Once fusion reaches its limit, the core collapses, triggering a supernova explosion. And what remains after this explosion depends on the original mass of the star. A neutron star will form if the remaining core is less than 4 times the sun's mass. A black hole, instead, will form if the remaining core is more than 5 times the sun's mass. So black holes are not holes at all. Instead, they're actually incredibly dense remnants of massive stars with gravity so strong that not even light can escape it. It's what gives it that black color appearance. Now that we went over the life of stars, how are they classified? Well, by temperature, the cooler stars are red, warmer stars are yellow or orange, like our sun, and the hottest stars are a blue or blue-white color. Now, besides different temperatures, stars also come in different sizes. Red giants are a main sequence star that has used up all of their hydrogen. This leads to helium atoms fusing into larger elements like carbon. Eventually, the star's core collapses inwards, and the star's outer layers spread out and cool. And those red giants are cooler on the surface and red in color. And it leads to a white dwarf, like we talked about. White dwarfs are a red giant that has burned up all of its helium. At this point, the fusion stops, the star shrinks, and eventually it cools down and the light fades entirely. White dwarfs are hot, white, glowing objects that are similar in size to Earth. Then we have red dwarfs, which are less massive and smaller in size than the Sun, and these have very long lifetimes. Supergiants come from massive stars. In these, fusion continues until there are no more elements left to fuse. Lighter atoms fuse into heavier atoms up to iron atoms. And eventually, these stars succumb to gravity and collapse as well. Now, during this collapse, the iron core explodes violently, which results in a supernova. Elements that are heavier than iron form in the supernova and then spread out into nearby space. Specifically, all chemical elements except hydrogen, helium, and lithium were created in the stars and from stars exploding. Now, as I just mentioned, when stars explode as supernovas, they scatter their elements across the universe. These elements, carbon, oxygen, nitrogen, eventually become part of new stars, planets, and even life itself. So when people say things like we're made of stardust, they're not being poetic, they're being scientifically accurate. We come from dead stars. The carbon that builds us is around in the universe from exploding dead stars. So we are a little bit of stardust. Now, these supernovas can be as bright as an entire galaxy, but only for a short little period of time. And the leftover core from a supernova is extremely dense. Now, if the star was originally less than 4 times the sun's mass, it forms a neutron star. And this is a city-sized object with neutrons spinning rapidly and emitting pulses of radiation. Some of these are called pulsars because they flash like cosmic lighthouses, emitting light and pulses. However, if the core is more than 5 times the sun's mass, the result is a black hole, which is a region of space where gravity is so intense that nothing, not even light like we talked about, can escape. All of the stars that we've described and talked about don't exist in isolation. They are parts of vast galaxies, which are collections of billions of stars bound together by gravity, not to mention all the other planets. And there are several types of these galaxies, including spiral galaxies, which are rotating disks of stars, gas, and dust, like our Milky Way that we're in. And these often contain many young stars. There are elliptical galaxies, which are egg-shaped or elliptical, and these are mostly filled with old stars. There are irregular galaxies, which are oddly shaped galaxies that are neither elliptical or spherical in shape, and these galaxies are deformed by gravity or collision with another galaxy. And last but not least, we have dwarf galaxies, which are smaller galaxies that have a few million or billion stars. And that brings us to the end of today's lesson. Until next time.